devices.
Okay, sir. Understood. Yes, sir.
है ना?
Yes, sir.
So from what we have seen till now, if we want to reduce leakage, what do? We increase the VT of devices. High VT devices, we say, would have lesser leakage. We use stacks and we decrease VB, because we saw that in a stack effect, there is some reverse or some source bias that is happening, which is leading to reduction in leakage. And we do that in terms of body biasing also. We say, let us apply reverse body bias in sleep mode. Sleep means in inactive modes, and forward body bias in active modes. Okay. So last time there was this question, I think, in the office hours, as to what is the difference between clock gating or power gating, clock gating and sleep. So for example, we could say that sleep mode involves much more than just enable signal on the clock gating path. Okay. So gate leakage, another slide just to give you an estimate of how the gate leakage changes. So when the physical gate oxide thickness was 19 angstroms, and we were operating at a VDD in the range of 1.8 volts, we had a gate leakage in the order of 10 raised to power minus 4 or something. Okay, not really significant. Huh? As we came to more finer, advanced geometries, then leakage started to become important. And as it is also said that in 65 nanometers and lower technologies, where the silicon dioxide gate is used, the TOX is actually less than 1 nanometer. And gate leakage, you will notice, increases very significantly. It becomes a very significant part of overall leakage, especially at room temperature. See, subthreshold leakage, we already observed, is dependent on temperature. So at room temperature, gate leakage becomes a very significant component. And therefore, we see that in advanced technologies, gate leakage is something that we are worried about. In the previous slide, we also saw the stack effect, and we saw that gate leakage over there is much very predominant. It was reasonably high component of the total leakage of that particular gate, depending on the input combination. You remember?
Yes, sir.
Okay. So,
sir?
Yes.
So you said that to decrease the leakage, we can decrease the body bias basically. So, but when we are seeing the stack effect, when we are seeing the stack thing, so we know that each of my basically NMOS is in different P wells right now.
It's in the same P well.
Yes, sir.
All the NMOSs are in the same P well.
Okay.
All the NMOSs are in the same P well, so their body is at ground, but their source is at Vx or Vz.
Okay.
So effectively, those transistors are in reverse bias because source voltage is higher than the body terminal voltage.
Okay. So, but how we are connecting the different P wells? I mean, how we would be connecting the different P wells of our NMOSs? Because
so just इस photo में ही देखो. If I make any more devices in the same P well, P substrate region, it is the common P substrate region, is it not? They're naturally connected.
Okay. Sorry, sir. So actually, I was asking about the for the N well kind of thing. I was thinking about
even N wells. If you are biasing all the N wells to the same value, and all N wells are then connected.
Okay.
Hai
Sir?
Yes, mother?
So this body bias, some place to our advantage when we talk about leakage, but wouldn't it create non-uniform currents, and that will lead to some uh, unexpected behavior of the device?
दोबारा से बोलो.
So because substrate is not directly connected to the source, then this means that if I stack my transistors, then they will all have different VTs at different point of times, at different point of operation. So wouldn't that change the current through each of those devices? And
Yeah. वही तो हमने दिखाया ना. In the stack effect, the leakage changes, so the current through the devices is changing.
so now the current is not uniform, like for modeling.
But KCL will still be followed, no, Madhur?
Yes, sir. It will be followed.
So whichever is the most resistive device, whichever can sink the lowest current, that will define the total current in the system.
Okay. Okay, sir. So,
Okay.
okay, sir.
Don't assume there is any current accumulation anywhere. KCL will still be followed.
Yes, sir. There is no accumulation, but as you said that the device that can sink lowest current will now be the limiting factor. Now,
Yes.
since the top stacks will, as we stack transistors, the top above transistors will become bad sinks. So, wouldn't that change my delays and all those
So
things?
when we will move to the combinational logic design, we will see that there is a way to design around the delays due to stacks. We'll see that. That is called tapered design.
Okay.
Okay. It will impact. Yes, for sure it will impact. But there is a way to handle it. We will handle it.
Okay, sir.
Sir,
Yes,
sir,
Vaishnav?
for all NMOS, sir, I understood that there is a common P substrate. That's the reason why we are grounding all the bodies to ground. Sir, but why is the Cadence giving us an option to connect the body to somewhere, sir, for an NMOS to be specific? Okay, I do understand that for PMOS we have that, but for NMOS, sir, why does the Cadence even give an option? Why can't it directly ground all the ground all the bodies of NMOS? Because
There is
okay,
a possibility in the technology to have what is called as buried envelope or deep envelope. That
yes,
deep
sir.
envelope is used to separate P-wells.
Yes, sir.
And when you can separate those P-wells by using that buried envelope, then what happens? You can actually
Then we
bias
can give
your
a body.
substrates
Yes, sir.
also separately. So for RF circuits or for some specific designs, designers may want to give that kind of area. And therefore, technology has to give you an option to connect the body terminal to different levels.
Okay, sir.
As a
But
designer, you have all the flexibility.
but the device which I select is NSVT-LP or PSVT-LP in Cadence, for suppose. So
Yeah. For
in
RF
that,
designs, also the same devices will be used, Vaishnav.
okay. So
The
okay,
design
sir.
methodology is different.
So there would be an option where I could enable a deep envelope.
Yes, you will have to draw it. You'll have to
Okay.
draw it on the in the layout,
Layout.
and
Okay.
then
Okay.
your P-wells will be separated.
Okay. Okay. Okay, sir. Thank you.
Okay. Raghav, you had a question?
So yes, sir. I mean, why would I be needing to like separate the P wells? I mean, actually, the whole point was that only, na? Right? Because by doing one, we were like.
No, suppose you do not want the stack effect. As Madhur was saying, that the performance would change. ऐसा हो सकता है ना?
So like as I could understand that the stack effect was coming into play because of our design only, because we had designing the NAND gate such that like they will be
So because of what happened because of that, Vx became higher than substrate voltage.
Yes, sir.
That is the reason why your leakage reduced, is it not?
Yes, sir. Yes, sir.
Now you do not want VT to change. What will you do? You will need to connect the substrate also to Vx.
Yes.
So then you will need deep envelope.
So I can do that in every P well we can connect to ground and different.
It's a huge area penalty. Huge.
Okay, yeah.
So you do not do it for digital circuits.
Okay.
This is, if done, it is only done for analog RF circuits, not for digital circuits at all. It's a huge area penalty. Okay.
So sir,
But
like
Cadence would always give you option to have that body terminal, and you may also want at some time to connect the body terminal. As a designer, you should have all the flexibility.
okay, so like for example, in the digital circuit, I would by default be observing this stack effect. I would get by the virtue of my design only because I'm designed like they would be PMOS CCD or NMOS and PMOS. So sir, like then why basically do I have to then why should I basically select the low VT devices? Because
Because you want speed.
yes sir, I mean because static effect, because due to stack effect I am getting the kind of the reduction in leakage. So why should I go, because earlier in the slide you were saying that 95 are basically high VT devices, but for the digital circuit I can go for the low VT then.
Yeah, so it means that you will have to use then more transistors if you do not go to high VT. You only use stacking to reduce leakage, then you will not be able. So for even an inverter, you will do stack of 2 NMOSs and stack of 2 PMOSs to reduce leakage.
Yeah, yes sir.
You waste area.
Okay, yes.
Instead, you do it like HVT devices.
Okay, actually I'm considering only the static CMOS implementation. That's why maybe.
Yeah. Okay. So let's quickly look at junction leakage. Junction leakage has 3 components. Basic, ordinary diode leakage, because there are diodes everywhere. Then band-to-band tunneling. What happens in band-to-band tunneling? So this is the diode leakage thing, where since there is a source and drain region and there is a depletion region there is some diode current that will flow. Reverse bias PN junctions will have some leakage. Then we're talking about band-to-band tunneling. What is this? Let us say that I apply, so we're talking about halo doping and all those things over here. Let us say that I have applied reverse body bias on my body so that I reduce leakage. What happens? The conduction band of one side starts to become aligned with the valence band of the other side. Okay, and if the depletion width is small enough, then electrons will simply tunnel from the valence band on one side to the conduction band on the other. That is called band-to-band tunneling.
Sir, why are these getting aligned, sir?
Aligned means, so initially they were like this. You applied reverse body bias. Initially they were like this. Then you applied reverse body bias and they went low. So now electrons will directly move from here to here. From here to here. Because you applied a reverse body bias, that is where it can happen. You expected that by applying reverse body bias, I will remove the subthreshold leakage, which you will. You will definitely reduce subthreshold leakage, but you will introduce band-to-band tunneling. Okay?
Okay, sir. Yeah.
Then there is also something called as gate-induced drain leakage. What does this mean? This means that due to some, so let us say there is this device. Let us say there is this device on the drain side. Let us go to whiteboard. So what happens is there is slight overlap between source drain and gate regions. So when you apply some voltage on the gate, there is some change in potential, the depletion region over here in this region, such that there is higher leakage in the drain. Why are we only talking about the drain? Because drain is at a higher voltage. Source and body are typically connected, shorted, but drain and body are at different potentials. So because of the electrostatic contours changing shape near the drain region, when you apply gate voltage, you see that the drain leakage increases, and that is reflected by this curve there. That is reflected by this red shaded region in the curve there. Okay, this is called as gate induced drain leakage. So we've looked at different kinds of leakages till now. Now, if I say that I want to, how do I put it? If I say that I want to now reduce overall leakage in the system, what all levers do you think we have? Hello?
So stack effect.
Huh?
Can you stack? Basically stacking.
Okay, you can stack,
The body effect.
due to which the body effect will come. Okay, what else?
So I mean, we can connect the body to different voltages if it is possible.
We can connect the body to?
Different voltages if possible.
For the PMOSes, it may be possible by, again, losing a lot of area. NMOSes, you will need to lose a lot more area to be able to do that. But let us say we still are able to create some voltage islands where we say that substrate voltages for inactive islands, you would want to keep at a different level so that leakage reduces. So that is body biasing across
Cluster
that is
of
body biasing across different circuit regions. Huh?
yes.
Okay. What else can you do?
Maybe
reduce the
try
width.
thicker oxides.
Hmm?
Maybe thicker oxides.
Thicker oxides. Okay, but
Reduce
thicker
the-
oxides, you will see that it will lead to change in speed. The speed would degrade.
Sir, long channel devices and high K dielectrics.
Yes, long channel devices, high K dielectrics, yes, so that gate leakage reduces. But a very important technique that you use is what is called as power gating. So when your entire circuit, you know that is not going to be operated, you put a set of these sleep transistors or header switch transistors on VDD. So your power gated block does not directly get VDD, it gets a new supply which is virtual VDD or VDDV. Okay. When you know that this particular block is going to be off or not operational, you can simply switch off these PMOSes. You can take sleep to 1. And when you take sleep to 1, what happens? The supply, the VDD supply is cut off. Okay. What it does necessarily require is that at the output, again, you put a gating with sleep bar, so that outputs do not lead to very high currents in the subsequent stages. Because the output, as you cut off the VDD, what happens? The outputs of this block will start to vary between 0 and VDD. Will no longer be at 0 or VDD. They will be anywhere, which can lead to high short circuit currents in the subsequent stages. To prevent that, what do? You put these AND gates out, you isolate the outputs. Okay. Now, it appears that this would reduce leakage. Yes, it will reduce leakage, but you should activate sleep modes only when you're doing it for a sufficient amount of time. Because toggling this sleep pin will in itself is it's a huge capacitance. The sleep would be running all over the place. It is a huge capacitance, and toggling the sleep pin in itself will consume some current. So that should not exceed the current that you are saving. Okay.
So, what is this output? What output I am taking here out from here? I mean, this would be the power gated
Like-
block would be my PDN or the PD pull up or the pull down network.
So let us say the power gated block only had the NAND gate.
Okay, okay,
So it
complete
is the
gate.
output of the NAND gate that we're talking about.
Okay, the complete gate. Okay.
You know?
So like we're saying in terms of the complete gate, not like the pull down or the pull up.
I'm talking about a power gated block, which means I'm talking about a full processor.
Okay. Okay.
I'm talking about a full memory there, for example.
Okay.
Okay.
So
That is where we did not say a circuit, we said a block.
Yeah, yes, details.
Okay. There was a question.
so
Nazar?
yes, sir. So even after I power gated it, I will still some previous stage will still be providing some inputs, right?
Yes, let the inputs come.
So
I am not using the outputs of this block.
yes,
Anyway,
sir.
I'm not using the outputs of this block. So let the inputs come.
Yes,
If my
sir.
VDD is not connected, it will not lead to any power consumption.
So still gate leakage will still be there because
Yeah,
and
that much you
MOSFET
cannot control. So full memory inputs are just going to 20 gates. There may be 20 inputs in a memory.
Okay, so even in this entire block, only the first stage of this block will be leaking from the gate.
We'll get the
And rest-
inputs ना बाकी तो सब कुछ के लिए वो float हो जाएगा बीच में
okay, yes. Okay.
है ना?
Sir, in this
Yes.
circuit, sir, if we are putting a condition on VDD, then even we are removing our stack effect, right, sir?
We are adding a stack effect. This VDDV is something like Vx, is it not?
Yes, sir.
We are adding a stack effect. We will need to size our circuits slightly differently so that this, or we'll have to have a huge capacitance on VDDV so that after power up, when you want to actually operate the circuit, stack effect doesn't appear in the delays.
Okay. Okay. Mm.
Okay, so that this VDDV is almost equal to VDD in active modes.
Okay, sir.
Okay. So what we looked at today was three kinds of leakages: static power being governed by subthreshold leakage, gate leakage, and junction leakage. We looked at scaling effects like DIBL, GIDL, and we talked about high K dielectrics also, that we use high K dielectrics so that physical gate oxide thickness can be higher and gate leakage can be reduced. And to reduce leakage, we discussed about using high VT, lowering VDD, we already discussed in the last class also, body effect, large length you mentioned, and then we also talked about sleep transistors towards the end. Okay.
So,
Yes.
so I have a doubt in the previous slide.
Okay.
Can you please? Yeah. So we are adding this PMOSes to cut off the connection between VDD and the our logic, right?
Yeah.
Now, when these PMOSes are turned off, so there would be some sub-threshold leakage also in those PMOSes. So
Yes.
should we,
Yeah, that will come. But overall leakage will reduce, no?
for our logic, the leakage will reduce, but that sub-threshold leakage of those PMOSes.
So it is again the same thing, Faisal. Look at it like this. There will be a KCL that will apply.
Yes, sir.
So if the power gated block does not allow sinking more current, how will more current go?
नहीं आए. Okay, sir.
है ना?
एक certain limit तक ही होगा वो.